All right, welcome to Unit 3, Trigonomic Functions. In this video, we're going to talk about the graphs of sine and cosine. All right, so first off, we have to understand that trig functions are functions. Functions have inputs, typically x values, outputs, typically y values. So it's important to understand that when you're working with any of the 6 trig functions, the inputs, what goes into a trig function, is always an angle. And anytime we look to make a graphs, we always use radians. So that's important to comment. I know you could use degrees, but formally we like to use radians when we talk about trig functions as functions. So those are the x values, right? So x values is just the letter that we typically call inputs. It's just kind of what's stuck over centuries. So the x values, the inputs for trig functions, are angles measured in radians. The outputs are ratios, right? They're y values, the y values. Now the y values, again, that's what we typically call outputs of any function. But the output of a trig function, again, is a ratio. And we should understand all of those different ratios based on everything we've learned. But we do base all trig functions off the unit circle. So inputs are angles and outputs are, well, it all depends. If it's sine, the output's the y coordinate from the unit circle. If it's cosine, the output's the x coordinate from the unit circle. And if it's tangent, the output is the y divided by the x from the unit circle. So that's what we really need to make sure we understand, is that we call inputs x, we call outputs y. But if we're working with the function sine, for example, sine of x, right? Because we put an x for the input. So x is an angle. And the output that we can typically call y is the y coordinate from the unit circle. If we're working with the function cosine of x, again, x, that's the input, that's an angle. And the output, f of x, again, which we do typically call y, is the x coordinate from the unit circle. And some kids get that confused because they say, wait a minute, the output's y. Why are you now telling me it's x? No, because I'm trying to use the function for what it is, right? The output of a cosine function is the x coordinate from the unit circle. We call that value y when we go to graph it, but what that represents is the x coordinate from the unit circle. And that may take a little bit of time for some of you to get used to. So let's dive a little bit more closer to functions. So before we look at sine, let's remember that we need the unit circle here. Oh my gosh, are we going to use this unit circle in this lesson a ton? The unit circle is like a guide, right? So the unit circle guides you to understand inputs and outputs for any trig function. Now this is exactly like an input-output table from back in your early days of algebra, right? For in the early days of algebra, we had input-output tables. An input-output table was simply a guide that tell you, hey, if x is negative 3, the output is 14. That's why. If x is negative 2, the output is 9. By the way, this function, in case you're wondering, you're probably not, but in case you're wondering, this function is x squared plus 5. So when I plug negative 3 into this function, negative 3 squared is 9, 9 plus 5 gives me an output of 14. If I plug in 0, 0 squared is 0, 0 plus 5 is 5. And I can even plug in decimals. 1.6 squared plus 5, 7.56, right? Because inputs and outputs are real numbers. So we're not constricted to having to use integers. We typically do because it makes it really easy to graph. But you can use decimals. You can even use fractions. I can plug 2/3 in. 2/3 squared is 4/9. 4/9 plus 5 is 49/9. Again, make sure you understand that. But the idea is that a input-output table is just a guide, so that when I go and graph, I know that there needs to be a point, a dot, at negative 3, 14. I know where to put that dot. I know there needs to be a dot at 0, 5. Again, that's the whole point of an input-output table, is that it's a guide to tell you where to put your dots. So we're going to use the unit circle as a guide to tell us what our input and our output is. So let's further explain this by looking more specifically at the sine function. F of x equals sine. Now remember, f of x is, again, always a fancy way of saying y. So, for example, and now, before I go any further, we have to remind you that the input x is an angle, and to be official, right, we use radians. We always use radians. I know you could use degrees, but we really prefer to use radians. So, for example, don't be afraid. Use your calculator. My goodness, don't be afraid. We could use our calculator. Just make sure we are in radian mode. And we could say, all right, what's sine of 1 radian? Well, I'm using my calculator right now. I know you can't see me, but sine of 1 radian is 0.84. It's a decimal. Oh, well, decimals are numbers too. And sine of 2 radians is 0.909. Okay, great. But instead of using values like 1 and 2, let's use values from the unit circle, exact values that we love. So let's start off with 0. If I plug 0 radians into this function, sine of 0. Now remember, what does sine of 0 mean? Sine of 0 means to look at 0 radians on your unit circle and tell me the y-coordinate. The y-coordinate is 0. So there it is. So my point becomes 0 is the input, 0 becomes the output, 0, 0. All right, now let's keep moving around this unit circle. Let's do pi over 6. Let's plug pi over 6 in. So if I plug pi over 6 in, sine of pi over 6 tells me to look at the unit circle. Again, it's my guide. And the output for sine is the the output for sine is the y-coordinate 1/2. So there it is. And if you like decimals, all right, 0.5, great. All right, let's keep going. Pi over 4. We could go around the unit circle. Pi over 4 is next, going around the unit circle. And again, I'm using the unit circle as my guide. So sine of pi over 4, sine is the y-coordinate. There it is, radical 2 over 2. Now, if you want to be able to graph this a little bit easier, you could grab a calculator to get a approximation. Radical 2 over 2 is about 0.707. And that might help us for graphing purposes in here shortly. But once again, keep going around the unit circle. Pi over 3 is next. So if I plug pi over 3 into, as the input into sine, sine of pi over 3 is the y-coordinate. That's the sine, right? That's the output. So that's radical 3 over 2. And if you're interested, that is approximately 0.866. That might help for graphing purposes. And then again, let's keep going. Pi over 2. If I plug pi over 2 in, sine of pi over 2 says look at pi over 2. The y-coordinate is 1. Okay. Now I could keep going around the unit circle, 2 pi over 3, 3 pi over 4, 5 pi over 6, but listen, I'm going to be here too long, so let's kind of jump the gun a little bit here. So let's jump to pi. Let's skip a couple values, right, go back to this input-output table, right? I went -3, -2, -1, 0, 1, 1.6. I was skipping values, right? First off, real numbers could be anything, so I skipped a lot of numbers. Just from going to 0 to 1, I skipped 0.1, 0.2, 0.3, 0.4, 0.5. So you're allowed to skip around a little bit. All right, so let's skip around a little bit here. So let's just jump to pi. If I plug pi into sine, the y-coordinate at pi, that's my output, is 0. All right, let's jump again. Let's jump to 3 pi over 2, just to kind of keep jumping around here. If I jump to 3 pi over 2, the y-coordinate, the output for sine is -1. And let's jump back to 2 pi. Now remember, 2 pi really is coterminal to 0. It's the same spot. But again, you're allowed to continue to go around the unit circle as many times as you want. So sine of 2 pi is, again, looking at 0 radians, which is 2 pi radians, same coterminal spot. And again, the y-coordinate there is 0. And I could keep going, right? I could keep going. I could go to 13 pi over 6. Right? That would just be going all the way around the unit circle and then go another, right? All the way around the unit circle is 12, 6, 2 pi. So going another pi over 6 would be 13 pi over 6. But again, that would be coterminal to just pi over 6. So the answer, if I plug 13 pi over 6 into sine, once again, the y-coordinate at 13 pi over 6 is 1/2. Or if you need to, 0.5. And again, I could keep going to, for example, to 5 halves. 5 halves pi. Once again, that's just all the way around a unit circle, 4 halves. 4 halves is 2 pi. And then going another half, right? So pi over 2 is actually the same as 5 halves pi. It's coterminal. But again, you could keep going around and around and around. So that would be a new input, but the output is going to be the same, 1, because at 5 halves pi, pi over 2, the output, the y-coordinate is 1. So this allows me to understand the idea of inputs and outputs. You plug in angles. What's the output for sine? The y-coordinate from the unit circle. Let's talk about cosine now. Let's shift gears and do cosine. This is where you got to be a little bit careful. Again, you got to really understand inputs, x, those are angles. Outputs, y, those are x coordinates from the unit circle. Now I'm going to call them y because that's an output to the generic function. But what it is, realistically, the output of a cosine function is the x coordinate. So again, let's start at 0 radians. So at 0 radians, the x coordinate is 1. Okay? And let's go to pi over 6. At pi over 6 radians, the output is radical 3 over 2, or again, 0.866, roughly, if you want to use a decimal. I prefer to be exact, but for graphing purposes, decimals might be better. Pi over 4, if I plug pi over 4 into cosine, the output is the x-coordinate, radical 2 over 2, 0.707. Pi over 3, if I plug pi over 3 into cosine, the output is 1/2. Again, or I hope everybody knows that's 0.5. Let's keep going. Pi over 2. If I plug pi over 2 in, the output is the x-coordinate, 0. And again, I'm going to skip some values now. Right? I'm not, let's cut to the chase here. I could skip some values. You're always allowed to do that with input-output tables. Nobody ever literally finds every single input. I mean, it's impossible. So anyway, let's jump to pi. That's 1/2 a circle. And the output, the x-coordinate from the unit circle is -1. And again, I'm calling it y. I know that because that's just a generic y is what we call outputs to any function. But in a cosine function, those outputs are very representative of the x-coordinate from the unit circle. So again, that's why you need the unit circle. It's like a guide. Let's jump to 3 pi over 2. So cosine of 3 pi over 2, the x value there is 0. And then let's jump full circle back to 2 pi. Remember, 2 pi is coterminal with 0, so I'm back to an x-coordinate of 1. And then again, I'm allowed to keep going, right? I could go to 3 pi, for example. So that would be going all the way around the circle, 1 pi, or 2 pi is all the way around the circle, 2 pi. Going another pi takes me to 3 pi. But 3 pi would be coterminal with pi, so again, the x-coordinate at 3 pi, which is the same as pi, is -1. So we call these functions, they're cyclic functions, right? Because they end up just repeating themselves. Because after you go around the unit circle one time, you just go around and repeat. You go around and repeat. You go around. So every time you go around, your inputs get bigger and bigger and bigger because you're going to be a bigger and bigger angle. But your outputs end up repeating themselves over and over again. Now, these functions are great, and these functions can also be transformed. So let's not get stuck in the fact that sine and cosine are the only possibilities. These functions can be transformed. And transforming functions is adding coefficients, subtracting, multiplying throughout the function. So let's look at a couple examples and let's work on inputs and outputs with these. All right, so in the next video, part 2, we will tackle how the heck do you solve or evaluate trig functions when you have these transformations. So stay tuned for the next video. Actually, I take that back. We will finish these problems, and then after these, we'll move into the part 2. I apologize. All right, so this first function is f of x equals 2 times sine of x, and they want me to evaluate what happens when the input is pi over 3. So I'm literally taking pi over 3, and I'm plugging in for x. So, and it's basically following order of operations. So I got to figure out what is sine of pi over 3. So, of course, I'm going to go to my unit circle. Sine of pi over 3, that's the y-coordinate, is radical 3 over 2. So I now have 2 times radical 3 over 2. So the 2 is from right here, obviously, and then I replace, again, once I plug pi over 3 in, sine of pi over 3 is radical 3 over 2. Now when I multiply, those 2's cancel, and I get a final answer of just radical 3. Nice and simple, really nice and simple. Let's try this next one, cosine of 2x. This time they want me to evaluate the function when x is 5 pi over 3. Now this time the 2 is inside the function. So before I analyze cosine, I have to multiply by 2. So when I plug 2 in, the following order of operations, again, that happens inside. So I got to do 2 times 5 pi over 3, and I get 10 pi over 3. So now, let me try to clean this up. I have cosine of 10 pi over 3. It's important that you realize in this first question, the 2 is on the outside. So I found sine of pi over 3 first, then I multiplied by 2. This time the 2 is on the inside, so I have to multiply the 5 pi over 3 by 2 first. Now I need to find cosine of 10 pi over 3. So again, I'm going to go to my unit circle, and I realize I don't see a 10 pi over 3. Well, 10 pi over 3 is here. We just got to find the coterminal angle. So if we take 10 pi over 3 and minus 6/3, 6/3 is 2 pi, we get 4 pi over 3. So 4 pi over 3 is the same thing as 10/3 pi, right? I hope everybody really understands that from what we've learned already. So once I realized that 10 pi over 3 is the same thing as 4 pi over 3, all I know is I want cosine. Cosine is the x value, which is -1/2. So my answer, my final answer is -1/2. All right, let's try this next one here. This time we have tangent of x plus 3. So notice here, the plus 3 is outside. So again, following order of operations, I'm going to do the tangent of x first and then just add 3 to that answer. So when I plug 4 pi over 3 in for x, the first thing I'm going to do is figure out what is tangent of 4 pi over 3. That's where I'll go to my unit circle. 4 pi over 3 is right here. And again, tangent is y divided by x. So I have to do the negative radical 3 over 2 divided by -1/2. Of course, the two negatives reduce and make a positive. And then instead of dividing by a fraction, I'm going to multiply by the reciprocal, 2 over 1. And I get the 2's reduced, cancel, and I just get radical 3. So again, following order of operations, tangent of 4 pi over 3 is radical 3. Then I have to add 3 to that, which radical 3 is irrational, so I really can't do anything more than this. This would be our final exact answer. Obviously, I could go to a calculator and type in radical 3 plus 3. It's going to give me a decimal. But because the part of it's irrational, this is really the best exact answer would be radical 3 plus 3 if I really want to keep things exact. All right, let's look at 3 more here. So this is interesting. This time the function is sine squared. I really want you to notice where we put the square. So let's just do a quick little mini lesson here. The problem is if we write sine squared like this, people are going to accidentally think that the x is getting squared. And there's a lot of confusion there. It's like, is the x squared or is the sine of x squared? So to prevent confusion from that, if we want the sine to be squared, we put it right here, which I know is kind of weird because you don't really square the sin, right? But you know, the easiest way to understand it is it's all a sine of x. So following order of operations, you find sine of x first, and then you square that result. Again, just to create, you know, mathematicians are lazy, right? We want to use as less as possible. So to prevent having to use parentheses and to prevent you thinking that the x gets squared, we put the square after the sin. That way we understand this is sine squared. So get used to that. We're going to see that a lot in the coming weeks. So just be careful that when we want to square the overall sine function, we actually, I would prefer this. I mean, if I invented all this stuff, I'd put the square outside parentheses. I think that's crystal clear. But the mathematical way that we do it is put the little square right there. So once again, I'm going to plug 5 pi over 4 in for x, or again, I could plug it in right here. But it's important that you understand that I'm going to do that first and then square. So again, it would best if I looked at like this. Sine of 5 pi over 4, and then square that value. So of course I'm going to go to my unit circle. I'm going to find sine. I'm going to find 5 pi over 4. 5 pi over 4 is right here. Sine is the y-coordinate, negative radical 2 over 2. So now again, following order of operations, I got to take the negative radical 2 over 2, and I have to square it. All right, first off, a negative squared is always positive. The square root of 2 squared is just 2. The 2 in the denominator squared is 4. That reduces to 1/2. There's my final answer. All right, let's try this next one here. This time I'm using secant, and I'm plugging in pi over 6. So again, lots going on here. First, before I do anything with that secant, I have to multiply pi over 6 by 4. Because again, following order of operations, do what's in those parentheses first. Then whatever I get for that secant, I will multiply by 2. So showing this in steps, it's 2 times secant of, and again, I'm going to multiply by 4. So I'm going to do 4 times pi over 6. That obviously reduces to 2/3 pi. Now I got to go to the unit circle and find 2/3 pi. Here it is right here. And I got to understand I want secant. Secant is the reciprocal of x. So if x is -1/2, secant would be -2 over 1 or just -2. So the secant part is -2. And then, of course, I'm going to multiply by that 2 out in front. and I get a final answer of -4. So it's really all about following order of operations and being extremely careful. All right, one more here. Again, we see that squared. So again, it makes a lot more sense if we say, okay, here's the idea. You got to find cosecant first, then you square it. So again, I'm plugging 2 pi over 3 in. So this is going to be 3 times cosecant of 2 pi over 3 squared. So following order of operations, I got to find cosecant of 2 pi over 3 first. So of course, I'm going to go to that unit circle, which is getting very sloppy. But 2 pi over 3 is right here. Cosecant is the reciprocal of y. So it would be 2 divided by radical 3. 2 divided by radical 3, just flipping over the y value. So again, if I'm following order of operations, I have 3 on the outside. I just discovered that cosecant of 2 pi over 3 is 2 divided by radical 3, all squared. Now, I know that you might want to get rid of that square root, but I would actually hold off on that because of what's going to happen next. Then I have to square that resulting value, which becomes 4/3. 2 squared is 4, radical 3 squared is 3. Then I can multiply 4/3 times the 3 that was on the very outside, and of course those 3's reduce to a 1, and I just get a final answer of 4. So these problems are really about following order of operations. You have to plug the angle in for x. Once you plug that angle in, do what you need to. Utilize the unit circle as your guide to tell you what that value is. And then again, continue on with order of operations. So these problems I don't think are extremely difficult, but you got to really, A, follow order of operations, and B, you've got to truly understand, like on this one right here, when you plug pi over 6 in, order of operations says you got to multiply it by 4 first, then find the secant. Whereas on, go back to a question like this first one, right here, once I plugged pi over 3 in, okay, I was done. Now I got to find sine of pi over 3. Then I multiply that by 2. All right, so this is the end of part 1. Sorry that I kind of stopped a little bit earlier. This is the end of part 1. And the next video, we'll start really taking a look at graphing these actual sine and cosine functions.